Hi, everyone, and welcome to our session about navigating the unknowable, creating resilience through security chaos engineering. We want to first of all thank RSA for hosting us and having us at this big event for showcasing the work that we've done in this space. We are really honored to be here today and are honored that you chose to watch our session. My name is Jamie Dicken, and I am the Director of Security Assurance at National Resilience, Inc. I lead up GRC, audit, and security awareness, and I have a huge focus on continuous security validation and a lot of the concepts we're going to talk about here today. My co-speaker is none other than Aaron Reinhart, the CTO of Verica, pioneer of security chaos engineering, leader of Chaos Slinger back at United Health Group, and co-author of a new O'Reilly report on security chaos engineering. We could not be more excited to present this talk to you today. We are going to discuss the challenges that we as an industry have been facing and how security chaos engineering is really the future that can answer a lot of our tough problems. We will also give examples of real world case studies that we both have been a part of, and then we will help you on your security chaos journey as well. If you're watching live, please make sure to use the chat window, and Aaron and I will be monitoring and answering your questions in real time. And with that, let's get started. As we all know, systems engineering is messy. In the beginning, we have these beautifully simplistic representations, either of what we want to build or what we think that we did build. But it doesn't take long for us to sour on our initially perfect creations. And it's not always our fault. Throughout a system's life, complexity has a way of sneaking in. And as time goes on, the problems compound as new change is introduced into the system, or even as our teams or our processes change. The reality is that after years of complexity, our systems become almost unrecognizable. And the outages and the incidents that we face just show that we aren't really keeping up with an understanding of our own systems. What we need is a radical new way to stabilize them and secure them if we're ever going to get ahead of this. And if you think about it, most times when you are changing a system, you're adding complexity, whether you intend to or not. And complexity itself isn't necessarily a bad thing. It could be really necessary for the use cases that you're trying to accomplish. But when you increase your complexity, you also increase the number of potential failure points that you have too. Complexity, it's more than just an engineering problem or an operations problem. It's also a security problem and a reliability problem too. As your system complexity increases, so does that opportunity for mistakes and accidents and misconfigurations that can lead to a breach. Year after year, for the last 10 years, the data and the cost of a data breach report has remained relatively unchanged. And we're still facing the cold, hard fact that almost half of data breaches are caused by human error and system glitches. Now, the good news is that these causes are preventable if we have a way of knowing that they've already happened. So therefore, that question really becomes, how can we proactively find these before an adversary does? In the past, we as an industry, we relied really heavily on system design and documentation to identify potential security vulnerabilities. We take these documents and we begin our threat modeling and identifying single points of failure and opportunities for latency. Unfortunately, in the world of complex distributed systems, this method alone isn't sufficient. It's still very valuable to do threat modeling, but relying on outdated documentation, relying on that alone, it's old school. Now, there are two real big problems with it. So first, your documentation is never going to tell you that a human being made a mistake. But next, think about when and how our documentation is typically made. Maybe it was made in the beginning of a project before a single line of code was written. If that's the case, then your documentation matches the system that was in an engineer's head, but maybe doesn't even match the system that was deployed to production. Or maybe that documentation does match what was deployed, but was it maintained throughout the system's life? The old school approach of only using documentation fails because the assumption is inherent that that documentation is correct that it's updated, and that it's complete. And I'm sure all of us have seen plenty of examples where that assumption doesn't hold. If your process of evaluating a system for security vulnerabilities or reliability issues is completely dependent on an outdated or incomplete representation of your system, your evaluation is ultimately going to fail. And there are going to be plenty of problems that you don't anticipate. I like this quote. Complexity scientist David Snowden reminds us that it's actually impossible for a human to document and model a complex system. The only way to understand it then is to interact with it. And that's going to be the core solution that we're talking about today. The answer to this challenge is not to just rely on our own recollection of our systems, but to use empirical data and learn from them. And that's really the heart of chaos engineering, instrumenting experiments that clearly, at the end of the day, remind us what our real system landscapes look like so that we can tease out those false assumptions. So Aaron, I'm going to turn it to you to tell us how to do things differently.
Right. I love that. I always like to say that in engineering, we don't believe in two things. We don't believe in hope and luck, right? We believe in good instrumentation and feedback loops, right? And that's what this is all about. It's really what it's about is it's about a new approach to learning and being proactive about proactively discovering, like Jamie said, that we made a mistake of an accident or that we've drifted beyond our security controls are no longer as effective as we thought they were because the system has drifted beyond the security's context. And so it's about being proactive and learning. So it's not about, so a lot of people think the way forward is really more about continuous fixing. It's not really about continuously fixing. It's about learning about how the system really works versus how it works, versus how we thought it works. And that's really in terms of like how we learn traditionally about how our system didn't really work the way we thought it did is through a series of outages, incidents, or breaches. And that's not a good time to learn. Chaos engineering is a proactive exercise and it allows us to actually learn instead of just continuously fixing the system when there's a problem. So how does the system become stable? So kind of like I was describing before, is that currently, how did that legacy system become so stable? How did the engineers become so competent or feel so comfortable with the system? Why does it have very few outages anymore? And why is it so quote unquote stable? Was it always that way? Is kind of the question. Is that most likely it was not, right? We learn about our system slowly becomes stable and well known through a series of surprises. If it wasn't a surprise, you would have fixed it, right? Or you would have taken care of it already. The thing is like we typically learn how the system really worked through those events, and we learn, okay, and then we take that data, we go back and we remediate, and then we run the system. Over time, we learn to understand the system better. But the problem with that process is that it comes at a very expensive cost, especially to customer. With chaos engineering, it's a proactive exercise of accelerating getting that kind of feedback without impacting the customer or the business. So it's also important to recognize that when there's an incident, an outage, or war room being launched, people operate differently. If you're not in security, you're probably freaking out. Because people are worried about the blame, name, shame game. And really, people worry about being blamed for being named for causing it. I knew I shouldn't have pushed that code, or I knew I shouldn't have made that change, and then being blamed for it. It's not a good environment for learning. Their cognitive state is overloaded already. So in chaos engineering, I like to break down, let's say, instrumentation into sort of two buckets. There's testing and there's experimentation. So testing is the verification of something we already know to be true or false. So in our world, it's either like a CVE, an attack pattern. We know what we're looking for before we go looking for it. Whereas experimentation, we're trying to derive new information that we previously did not know. You could think that's why experiments in the form of the scientific method hypotheses, is that we're trying to discover the unknown behavior in the system. So here's the definition of chaos engineering. Chaos engineering is the discipline of experimenting on a distributed system by injecting turbulent conditions to learn how the system responds. So another way of saying this is that it's sort of the discipline of proactively introducing turbulent conditions into a system to try to determine the conditions by which a system will fail before it actually fails. So we can learn and remediate it, and the problem never actually manifests. So it really is a proactive act. That's what really makes this unique, is that it's not about mean time to detect, mean time to respond. We're proactively doing these exercises when there is no real problem. When we have the opportunity to learn without playing the blame, name, shame game. Because we can't learn during an active incident because it's about get that thing back up and running, or like we have an ongoing attack. We got to, it's about the mindset. The cognitive load is not there for you to be able to learn. So security chaos engineering, really what we're trying to do is that we're trying to proactively understand and discover. So in modern security, we have this issue where, or modern engineering per se, was that as a builder, I need the flexibility and convenience to constantly change something. I'm constantly changing it because I'm attempting to deliver on business requirements to deliver customer value. So I'm constantly changing in order to do that. Well, security is a context-dependent component. So security you must understand the object and the context about it in order to know what needs to be secured. The problem is that as we're delivering on and building it from an engineering perspective towards customer value, the controls are often not moving along with it. You start to diverge. And what we're trying to do with chaos engineering is expose that drift before an adversary can actually take advantage of it. And that's really what we're trying to achieve. So we often actually misremember what our systems really are. And like Jamie said, there's just over time, we don't recognize it because we can't rock all that information in our heads, like all the changes and all the different teams and all the different pieces of the system moving and changing. It's great. It's an opportunity for mistakes. I mean, we're human. We're going to err. That was always part of the equation. But like it increases as the more changes we make to the system, the opportunity for accidents, mistake, cognitive misalignment is there. So really one of the areas that I know Jamie and I have this in common is that we focus on chaos engineering is really about continuous verification. We're continuously verifying the system works the way it's supposed to. It's not, we're not attacking it. What we're trying to do is we're introducing questions into the system. Hey, I believe under X conditions, Y is what the security is supposed to do. So we're introducing that failure mode or that fault into the system to verify that control works the way it's supposed to. And we never do a chaos experiment we know is going to fail because we won't learn anything. So here's some brief use cases. Actually, in the O'Reilly report that we're going to have a link to at the very end, that Jamie and I are both a part of, it goes into more depth with these use cases. But some great use cases are incident response, security observability, control validation is also, I know Jamie and I both experimented. We got a lot of value in that. But it's also important to remember that every chaos experiment, whether it's for security or availability, has compliance value. So make sure that to keep the outputs in a high integrity way. So there are some differences. So a lot of questions that Jamie and I get, and a lot of people in the security chaos engineering space get, is what is the difference between red teaming and sort of some of the traditional exercises like red teaming, purple teaming, pen testing, and breach and attack simulation and security chaos engineering? There's a wide definition of what those things are, but often pen testing, red teaming, purple teaming are most often done at the top 5% of the application portfolio, and they're not. They're very. All these things are very valuable. Do not misconstrue what we're saying. What we're saying is there's a difference in approach and value. In that we're not trying to attack it. We're not trying to get in. We're not trying to simulate some kind of attack in the system. We're taking into account the complex nature and all the interacting parts of a distributed system into what we're doing. And because if you start sending attack information, you're sending a lot of information to the system. It's hard to figure out what worked, what didn't, with all the noise. The signal to noise ratio is quite large. What we're doing with security chaos engineering, introducing very small perturbations or faults in the system one at a time, trying to determine did it work the way it's supposed to? That way we can look at the broader lens and understand what worked, what didn't, and then repeat and continually run the experiments. And if you're looking for more information on the differences, there's some great articles out there as well as in the book. Jamie, back to you.
All right. Well, thank you, Aaron. So there are several companies that are implementing security chaos engineering today, and we are continuing to see that number increase, which is fantastic. Cardinal Health, where I used to work until March of this year, was among those that began implementing the discipline about 2 years ago. And so of the 4 use cases that Aaron described, the one that really drove our adoption and our investment in the team was security control validation. At the end of the day, we, like so many other companies, had really put our faith in the idea that our tools, our technical designs, and our technology standards that we had kept us secure. And it's not that we didn't trust our people, but look at the data that we see year after year. Our leadership at Cardinal Health realized that we needed a new approach to security, one that focused on building and maintaining security controls, but also validating that they stayed in place, that they didn't degrade over time. And also a way to get after that 48%, which we felt was very preventable. So the summer of 2019 was when Cardinal Health invested in a team to build security control validation and to implement security chaos engineering. So I came from a software development background, and I was brought in to build a team of multidisciplined engineers that had diverse technical backgrounds. And that to us was really key, that everybody came from a different background. The reason was that we wanted to be able to make good guesses about where some of our existing security control gaps were so that we can prove value right away, start working on remediations. And that's why when the team first launched, we had collective expertise, not only in software development, but security architecture, systems architecture and design, systems administration, network engineering, cloud engineering, risk, and privacy. So a lot of times what we ended up doing was we would build some of our own security control validations ourselves. A lot of common tools on the market today have APIs that are publicly available that you can actually configure, you can actually query for its configurations. Other times we would take a look at either open source or commercial off-the-shelf products if we could not write a script that met our needs. But we got to make some of those really good build versus buy decisions to do what was right for the company. Ultimately, at the end of the day, our goal was to identify unknown technical security gaps and partner with the organization to remediate them before an adversary found them for us. I want to talk a little bit more about how we did it. So as exciting as it would have been to just, get access to every system and every project and go nuts looking for technical security gaps, we knew that we needed a disciplined and repeatable process that accomplished 3 things. So first is that our process had to identify indisputably critically important deficiencies. It didn't do us any good if my team went after a bunch of gaps that at the end of the day, the business decided wasn't worth fixing due to the risk or they weren't a high enough priority. So we knew we had to establish some benchmarks that were relevant to our company and to our systems. This way, when we established benchmarks, the gaps that we found, we wouldn't identify them just on an arbitrary basis. And these benchmarks wouldn't be just merely theoretic best practices that in reality turned out to be too lofty to achieve. So that was one. Second was that our process needed to be big enough to see the big picture of the technical security gap and detail where we saw this. The challenge we had was that previously Frontline's engineers in different areas either hypothesized that we had gaps or they had seen evidence, but what they really lacked was that visibility into how widespread something was and all of the detail that was necessary to document it and drive it to remediation. And so we knew we needed to do something differently. And then finally, we needed to make sure that whatever technical gaps we identified and drove to remediation weren't just unknowingly reopened in the future. We wanted to make sure that if we were fixing things now, that we didn't find ourselves in the same place come later. So with those goals in mind, we created a process that we called continuous verification and validation, or CVV for short. It's simply put, on a regular basis, we wanted to continuously verify that our technical security controls were in place and validate that they were implemented correctly. And that process really included 5 steps. First, we obviously had to identify which security control we wanted to validate and which one we were going after. Second was that we had to establish the benchmarks by which gaps would be identified. So to give authority to our findings, we largely used the standards that were set forth by security architecture and our cloud architecture teams, and that were approved by our senior leadership. If those standards didn't yet exist, we still could proceed. We would still partner with all of our relevant stakeholders and start to brainstorm what our recommendations would be. And after that, we would socialize those. And so what was key about that was that we started to set the requirement that if we found gaps, either those had to be remediated or we needed to get visibility to our leadership so that they could accept the risk. But this gave us a treasure trove of data that could help move the needle on our security posture. The third step was when we got to do the fun part, the security chaos engineering part of implementing the continuous checks to make sure that our systems were adhering to our benchmarks. Again, either we would write our own scripts using APIs, or we would look for tooling of some kind. After that, we created a dashboard that illustrated the real-time compliance with our benchmarks. And this was really key because it did 2 things. So one is it let us on demand pull up, have an understanding of where we stood with that security control across the enterprise. And second is it actually fed some reports that we would show to our senior leaders so that they were aware of what our real security posture was and they could make decisions that were based in real data. And then finally in our process, if at any point we had identified that adherence to our benchmarks decreased, that's when we would place an issue in our risk register. And we had some really good governance processes that would drive that to remediation. So that's that process in a nutshell. But the beauty of it was that this process wasn't just done in a vacuum. It wasn't fun and experimentation just for the sake of fun and experimentation. Security chaos engineering became a means to drive real security posture enhancement. So what we did was we fit ourselves into a process where once we identified mistakes or misconfigurations, we would partner with the relevant IT teams and with the enterprise to get a remediation plan in place and to actually execute on that. And then after that, not only did our security posture increase, but then we had that continuous monitoring in place afterwards to make sure that our security controls didn't degrade over time. So for Cardinal Health, security chaos engineering became the start to creating long-term confidence in our security posture. So that is the Cardinal Health story. So Aaron, I'm going to turn it over to you to talk about your work with Chaos Slinger.
Thank you, Jamie. I always love hearing the Cardinal Health story. It's such a great story of transformation. So Chaos Slinger was the first open source tool for United Health Group. It was actually the first ever sort of implementation of Netflix's chaos engineering to cybersecurity. And so the main example of Chaos Slinger when we released it was what we called Port Slinger. We need an example that kind of everybody could understand, and misconfigured or unauthorized port changes are a common thing even today. And most people kind of understand what a firewall is and kind of what you do in those processes. So our expectation was with Port Slinger, or when a misconfigured port would be inserted into the system, is that our firewall would immediately detect and block the change to be a non-issue. Well, what we were finding, we built Chaos Slinger to proactively inject either an open or closed port where that wasn't already open or closed into our Amazon EC2 security groups. And what was interesting is that the firewall only detected and blocked it about 60% of the time. And what's important to remember is that there was no issue, no war room, no incident. We were able to proactively do this and learn that, oh, there was a drift issue between our non-commercial and commercial software environments. Okay, we fixed it, non-issue, because no customer was impacted because of this, because we fixed it before it became a problem. The second thing we learned was that the configuration management tool, the cloud native one that we were using, caught it and blocked it every time. So it was like, wow, we didn't expect that to happen. So that was the second learning. The third learning is that we had a homegrown kind of, think of it as like a SIM, kind of where we built our own tool for like security logging. And I was not very confident that we were actually going to be able to derive alerts because we were new to the cloud at the time. But that actually happened. We actually drove an alert to the SOC. The SOC got the alert, but the analyst didn't know which AWS account it came from. They didn't know which account it came from. Now, it is, as an engineer, you can say, well, I can map back the IP address. I can find out where it came. Yeah, you can, but that could take 15 minutes. It could take 30 minutes, right? Or if SNAT is applied, it could take longer, a lot longer. And if 1 minute of downtime is $10,000 or even $1 million, that gets very expensive. But guess what? There was no loss. We were able to proactively say, hey, all we have to do is add metadata pointers to the alert, and we're good. And we'll know. Like, it's like, we fixed all these things because we're able to learn proactively and not have to respond and react to an ongoing problem. We're able to fix it before it became a problem. That's the key part of this. And one other thing I want to add to this is that we weren't simply reading a config in what we're doing. What Jamie and I are talking about, we're exercising it, which is a big difference.
So as you can see, Aaron and I obviously believe very strongly in security chaos engineering. And we believe that the more companies that adopt this practice, the more resilient all of us are going to be, as we'll be proactively identifying security and reliability issues before they become incidents. So we'd like to turn the conversation at this point into how everyone in the audience can implement this practice. So first, if you're thinking that what we're discussing is just too cutting edge for your organization, first, I want to encourage you to adjust your mindset here and think about this almost as you would just like standard testing. Yes, there is an experimentation element to it too, but for the sake of adopting and moving towards it, let's first think in that testing lens. So with my background in normal software development, what really attracted me to security chaos engineering in the first place was that the parallels between security chaos engineering and testing were just too profound to ignore. So you can think about security chaos engineering, or think about the Cardinal Health CVV process as basically the systems level equivalent to a regularly scheduled automated test suite. It's just that instead of verifying that your code meets the functional requirements of the system, you're testing that the system meets its security and its reliability requirements. So both sets of tests you can run on a continuous basis. You can run them in prod or non-prod, depending on your scenario. But you could also implement it even in like a test-driven development model. As new systems are coming on board, you can start to identify and engineer what experiments you're going to run. And as that system matures and you start to see your experiments passing and giving you the results that you want, that's how you know that the security and resilience requirements are going to be met. And so when you think about it this way, and you think about it kind of from that testing lens, security chaos engineering ceases to be that esoteric practice that's too cutting edge for a modern enterprise to adopt, and it really becomes logical and practical. I like to think about my days as a software developer, because I never would have shipped code that didn't go through a slew of testing. I would have written my own tests that exercise that functionality. I would have made sure that all the tests in my CI/CD pipeline passed. I would test it manually or even in an automated way in a non-prod environment. And then even after I deployed the code to prod, I would smoke test and do what was safe there. And that became a standard practice if you think about it. And what really made me wonder when I first joined security chaos engineering and started implementing it was, why should the systems world be any different? Why should we not go through those same types of tests? And so as I see it, just like the world of software development first adopted these practices, The systems engineering world is going to have to do the same. So once you've gotten past that mindset and you're ready to experiment, it really is possible to start small. I think one of the biggest myths about security chaos engineering is that you need this super complex, system-wide, highly disruptive experiment that you wreak havoc in production. And therefore, you need to have a business case, you need VP approval, and all of those other things. That's a myth. You can start a lot smaller than that. So let's reflect on what Aaron had said earlier. Some of the primary use cases for security chaos engineering include incident response, security control validation, compliance, and observability. You can test those without inflicting mass chaos on your own company. So for example, say you have a control that watches for public storage buckets and closes them automatically. Go ahead and perform that experiment. Open up a public bucket and see what happens. Do your controls close it like you think that it should? What's the time frame? Does that match what you have documented? Say you have a detection in place that discovers rogue access points. What happens if you connect one to the network? One that's clean, that you own, is safe, but does it get detected? Is there enough information available in the logs so that a human can see it and respond to it? If you have a playbook for when an unapproved firewalls rule is open, or when any protection systems stop being configured to protect, go ahead and do this. Now, do it carefully in an environment that's pretty low risk to start, and make sure to revert what you did, but test that you see this happen in your logs. Test that an alert actually does fire. Test that somebody actually responds to it. All of those are security chaos experiments. And if you're thinking that even that experimentation is a little bit too advanced for your company and your company's appetite just yet, then start to do something even lower impact. You could do something very similar to the Cardinal Health CVV process. Just start by querying your security configurations and figure out if they match what you believe that they should. So for example, if you have endpoint agents that are deployed to all of your employees' laptops, are they deployed everywhere? Are they actually running and in a healthy state? Are they on the right version, or at least N-1? If they have security policies, are they the policies that you believe shouldn't be in place? These types of mini experiments at least peek at what's out there and have virtually no impact. So they're great places to get started. So where do you begin? First things first, Aaron and I have both been talking. There is a brand new O'Reilly report that was published this past fall, all about security chaos engineering. And the link is here. The ebook is free, so go ahead and download that. It was written jointly by Aaron and also Kelly Shortridge. And it covers not only the basics, but it has additional information on the Cardinal Health use case and has a ton of contributing authors. So you can hear stories from other really, really smart people at companies like Verica and Google, and Capital One has a great case study in there as well. So it is really a wealth of knowledge. It's only 90 pages long. So it's a short read. It's a great read. Read through that and you will understand the basics. Next, after that, start to look for areas in your security programs where confidence is critical, and start thinking through how you would instrument experiments there. Maybe even start implementing a couple of experiments, maybe using some of the examples on the previous slide, or anything that's really low risk. I do recommend starting low risk so that you get the feel for the discipline and how do you set up an experiment, and you don't run the risk of halting your progress before you really even get started. But learn the basics and you'll be able to grow from there. After just a couple of experiments, I can almost guarantee you that you are going to have findings and that you're going to learn new things about the way that your systems actually function. And that's great. It's great to learn now, like Aaron said earlier, in a time where you're not really worried about being named, blamed, or shamed, and you can be proactive. So once you have those learnings, that's going to let you do things like prove value in security chaos engineering, maybe create a business case to expand the practice. Maybe it'll even get you some additional access to do some experiments in other areas where you wouldn't normally be able to have that access. And at that point, you can start to increase the breadth and your complexity of your experiments as well. And there you have it. So as you can see, security chaos engineering is a field that it may seem esoteric and out there, but at its core, it's really logical and it's really simple. Instead of allowing the vast complexity of our systems to overwhelm us and create so many opportunities for accidents, mistakes, and misconfigurations, really the answer is to flip the model on its head. Instead of relying on our documentation and our preconceived notions, we can go in, eyes wide open, ready to learn, ready to experiment, and learn from our systems and see what they really are and not what we hope they would be or what the pictures in our documentation say that they are. And through that testing and that experimentation, we get to identify opportunities to proactively secure and stabilize our systems and get us away from the reactionary fire drills and the engineering practices we have today. In case you missed it, here is a link to the book one last time. It's vertica.io/SCE-book, and it is free. And we really hope that this session was valuable for you and that you learned something. Here you're going to find our contact information if you want to continue the conversation. Thank you again to RSA for hosting us. This has been a fantastic experience. We always love coming here. And thank you to everybody who listened live, and enjoy the rest of the conference.